Hello everyone. So I just typed in Google. I said, why science proves nothing? Question mark. First thing on the top of the page is why science does not prove anything. Let's go ahead and open that, and we're going to go ahead and read a little bit about what it's talking about, okay? Why science does not prove anything. We often read that science has proven something. However, for a scientist, this is an immediate red flag, as we should never use the term proven in a scientific context. Here I will explain why everyone should see red flags when they read science proven or scientifically proven. Why we can't use the word proven in science. Okay, it says observations are never perfect, interpretations are never perfect, a truth needs a context and cannot be extrapolated beyond that context. Information is often incomplete. Okay, you seeing this? This is very important, right? Because we have a lot of cyberbullies going around the internet saying everybody's stupid, that thinks that there's energy in space that can be used to power the infinite will, the infinite will works of nature can power our machines, right? And they're like, prove it to me. That's an absolute scam to say that. For someone to say that is asking an experimenter to participate in a scam. That's one way of thinking about it. I don't know how else to think about this. I'm going to share with you what this says, okay? We'll let this article do the talking. And you know what? There's millions of articles like this. This is not the only one. This is shared by the greatest philosophers on the planet and throughout history. This is a known fact. It's a fact. Why we should never use the word proven within a scientific context. Proven means that it is absolute. There is absolutely no chance that there is an alternative explanation. There are plenty of examples where people were convinced they had proven something, only to discover later that they were wrong. Our observations often play tricks on us, and even though we do everything possible to verify and make sure we are right, it is never 100% certain that your observation and the interpretation are correct. If we take a simple example and look at figure 1a, we are easily convinced that the two gray squares A and B are different shades of gray. If we designed a study and asked a group of 100 individuals, the vast majority, maybe even all of them, would agree with this statement. However, the GIF below, figure 1b, will show that this statement is wrong. The context of everything else around it and the shade that is introduced makes our brain think that the colors are different. Our conclusion was influenced by everything else we were observing. Carefully removing all of those factors will reveal the real truth. This is just an illustration that our eyes can play tricks on us. Figure 1b, gray shaded boxes GIF. Below are two more examples. In figure 2a, focus on the dot in the center and move your head back and forwards. This gives the illusion that the circles are moving, even though they are not. The next figure 2b, consists of perfect lines and squares, even though our initial interpretation would lead us to believe otherwise. The bottom line is that our observations are not perfect. For a long time, people thought the earth was flat. They were convinced it was flat. They thought it was proven until it was demonstrated that it was not. Another example is that miasma theory, which proposed that all diseases were transmitted by bad air, often referred to as dark air or black air, until it was demonstrated that diseases were caused by microorganisms. Another instance is related to heat transfer. It was thought to be a substance or invisible gas which flowed from hot materials to cold materials. Scientists in the 1700s were convinced that caloric would flow from one material to another. When you place a hot piece of metal on a cold one, the cold one will become hot. It was thought this was because caloric was flowing from the hot metal to the cold. You could even feel it with your hands. No scientist considered it proven. Oh, so scientists considered it proven. The bottom line is that our observations are not perfect. Why science does not prove anything? There are 4 main reasons why science cannot prove anything. Difficulties with observation, difficulties with interpretation, context, incomplete information. Now, you should read this yourself, but we'll go ahead and go through some of this. The above examples of optical illusions are a clear demonstration that eyes can play tricks on us. The same is true for our measuring devices and their operators. In science, much is done to prevent wrong observations. Wrong observations come in many different shapes and forms. It may be wrong because it is not actually measuring what we think we are measuring, or the measurement may not be reproducible. We refer to this as validity and reliability. Of course, researchers do everything they can to make sure measurements are valid and reliable. There are calibrations, verifications of data, replication, confirmations by independent measurements, and so on. But we can never completely eliminate error. Difficulties with interpretation. But imagine that the data collected is free from all error, a hypothetical situation. Our mind that has to interpret this data is not. We see the world in a way that is influenced by many factors, our genes, culture, education, etc., etc. There are many forms of bias that will creep in as a result of this. Again, researchers do everything to minimize bias. They are trained to recognize potential bias and avoid it. But bias is everywhere, and it can never completely be avoided or removed. An example of bias is publication bias. Studies with a positive finding, for example, supplement X has an effect, are more likely to be published than studies without a positive finding, supplement X had no effect. Of course, both outcomes are important, but if only the positive outcomes are published, this will result in a bias. So even when our measurements and observations would be free of any error, the interpretation of the data is not. Context. To build on this interpretation issue a little more, a truth requires a context. So if a statement is true, it may only be true in a very specific situation. For example, carbohydrate feeding improves performance. It very likely does during prolonged exercise, but it may not do this during sprint performance, such as a 60 dash. Any general conclusion that seems to generalize more is less likely to be true. There are always situations where it may not be. So we can't say something is proven because there may always be situations where this may not work. Pseudoscience. Incomplete information. Sometimes we simply don't have the right data or sufficient data to come to solid conclusions. We hear scientists often say we need to do more studies or we need more data. If we have 2 studies and they don't have exactly the same results, it would be good to do a 3rd study to find out why. However, resources and time are not unlimited. Science is moving slowly, more slowly in certain areas than others. As a result of both of these factors, the meticulous work of a single research project sometimes takes years, and one research project may only unravel a very small piece of the puzzle. Even in areas where there is apparent agreement, and we must be aware that it is possible that at any time new and contradictory information could arise. The more studies we have with similar findings, the less likely it will be that we will ever have to revise our thinking. But we can never be 100% certain. We can draw conclusions and we can be confident that these conclusions are very likely correct, just never 100% certain. So can we never draw conclusions? Can we not be confident about anything? Of course we can. We can draw conclusions and we can be confident that these conclusions are very likely correct. We can be confident, incredibly, absolutely, positively confident. Just never 100% certain. There are a number of great quotes by the great scientist and thinker Richard Feynman. Richard Feynman! Nobel Prize winner. He's quoting Richard Feynman here. Caltech professor, Pasadena, California, and Nobel Prize winner. I can't believe he's quoting Richard Feynman. I always talk about Richard Feynman. Richard Feynman is one of the #1 people I quote all the time. Richard Feynman is the gentleman that said there's enough energy in a cubic centimeter of space to power the world. I'm paraphrasing, but enough energy to power the planet, right? It's been said many different ways, but I'm saying it in the energy context because we always talk about how we need lower cost energy, right? Richard Feynman. We absolutely must leave room for doubt, or there is no progress and no learning. People search for certainty, but there is no certainty. Hear that? This is very big, okay? It's as big as the universe. It's as big as our imagination, which are both the same size. We absolutely must leave room for doubt, or there is no progress and no learning. People search for certainty, but there is no certainty. So bullies, cyberbullies get on the internet and say, prove it to me, prove it, you can't prove it, you can't prove it. And I think they're looking for certainty, but Richard Feynman's saying we all are looking for it, but we don't have to be a bully about it, okay? That's the important thing. And we must never put other people down. We must lift people up, lift one another up. That's what we have to do. That's a humanitarian effort, and it's part of worldwide solution-oriented collaboration, which we must be on a shared mission together so we can stop having wars and stop causing harm to one another, right? We're here to help one another. That's what we are here for. All of us are here for that. And we must start learning that right away in school, right away. I have approximate answers and possible beliefs in different degrees of certainty about different things, but I'm not absolutely sure of anything. I'm going to read that again. I have approximate answers and possible beliefs in different degrees of certainty about different things, but I'm not absolutely sure of anything. Scientific knowledge is a body of statements of varying degrees of certainty, some most unsure, some nearly sure, but none absolutely certain. Can we never use the word proven? We can. There are certain contexts where the word proven is justified. It is possible to use the word proven in situations where there is 100% certainty. In maths and in logic, this is possible. 1 + 1 = 2 in all situations. This is different in science where we will never achieve 100% certainty. Of course, it is baffling that there are so many people who know that something is true, even though they don't base it on any scientific evidence or any other evidence. There is no effort to even check it is true. They just know it is. Scientists spend so much time and effort checking if what we believe to be true is really true, and then end up with an answer that is likely true, but they are still not 100% certain. Read also the article on the Dunning-Kruger effect. A little knowledge gives people huge confidence, and people quickly draw conclusions and shout about it. Whilst learning more and knowing more will actually raise more questions and increase uncertainty, and it requires a lot of knowledge before you can climb out of this valley of despair. So next time you read that science has proven something, you can be certain that you are not dealing with science. Bingo! Right there. Hello. Thank you very much. Thank you very much. Thank you very much. Okay, bullies, it's time to go to gentle school, learning how to be gentle, kind, caring, supportive collaborators. And there's no positions for bullies anymore. Those are all closed. Those positions are all closed off. Done. Okay? We should never hear the words "prove it to me" again. That's just a mean thing to say. It's irrelevant, and it's asking someone to participate in non-science. Okay? Saying "prove it" is asking people to participate in non-science. Okay? That's what that looks like to me. You can tell people to share their experiments, share their results, share how they replicated something, share how they approached it, and that's what this is all about. It's about collaboration and sharing, right? You know, if someone wants to just show a bunch of magnets spinning around and producing really high voltages and high power, that's fine too. It's more helpful when you can share theory about what's taking place, write about it, share thoughts and ideas. But, you know, we all have strengths, and we do our best with the things that we're not strong with, and we try to strengthen our weaknesses and strengthen our strengths as well. And together we can support each other and help each other. But don't forget, next time you read that science has proven something, you can be certain that you are not dealing with science. Right there. Have a great day, everyone. See you in the next video. Bye.